Section 6.4, Graphs of Logarithmic Functions. In this section, you're going to identify the domain of a logarithmic function and graph logarithmic functions. First, finding the domain of a logarithmic function. Before working with graphs, we will take a look at the domain, which is the set of input values for which the logarithmic function is defined. Recall that the exponential function that we defined as y equals b to the x power for any real number, x and a constant b is greater than 0 and b is not equal to 1, where the domain of the exponential function was all of the real numbers from negative infinity to positive infinity. The range of the exponential function was from 0 to positive infinity, x inclusive of 0. In the last section, we learned that the logarithmic function y equals log base b of x, it's miswritten here, so y equals log base b of x, is the inverse of the exponential function y equals b to the x power. So as the inverse function, we know the domain of the logarithmic function is going to be the range of the exponential function. So the domain of the logarithmic function is going to be from 0 to positive infinity, x inclusive of 0. The range of the logarithmic function is going to be the domain of the exponential function, and that is equal to negative infinity to positive infinity. The domain of the logarithmic function is from 0 to positive infinity, similar to the range of the exponential function. And the range of the logarithmic function is the domain of the exponential function, which is from negative infinity to positive infinity, or all of the real numbers. Transformations of the parent function y equals log base b of x behave similarly to those of the other functions. Just as with the other parent functions, we can apply the 4 types of transformations: shifts, stretches, compressions, and reflections to the parent function without loss of the shape of the parent function. In graph of exponential functions, we saw that certain transformations can change the range of the exponential function y equals b to the x power. Similarly, applying transformations to the parent function y equals log b of x can change the domain of that function. When finding the domain of the logarithmic function, therefore, it is important to remember that the domain consists only of positive real numbers. That is, the argument of the logarithmic function must be greater than 0. So we agree that the argument is basically the x value here must be greater than 0. Let's look at some examples to find the domain of the logarithmic function. The first function here, f of x equals log base b of x plus 3, that is the argument. We're going to set the argument greater than 0, and then we're going to solve. So we subtract 3. We end up with x is greater than negative 3. So we convert that into an interval notation. That will give us the domain is from negative 3 to positive infinity. If you're in doubt, you can basically sketch a graph really quick for that one. In a similar manner, we're going to find the domain for the next logarithmic function, f of x equals log base b of 5 minus 2x. We take the argument again, 5 minus 2x, and we set it greater than 0 and solve to get the domain. So if we solve this one, I am going to first subtract 5 from both sides. So I will get negative 2x is greater than negative 5. And now I'm going to divide by negative 2. And because the division happened with a negative number, I have to flip the inequality sign. So I will have x is less than 5 over 2, because the negatives are going to cancel one another. Now, if you want to convert into an interval notation, the domain is going to be from negative infinity to 5 over 2. So that is the domain of the second logarithmic function. Graphing logarithmic functions. So in order to graph a logarithmic function, we begin with the parent function, y equals log base b of x, because every logarithmic function of this form is the inverse of an exponential function with the form y equals b to the x power. Their graphs will be a reflection of each other across the line y equals x, as we learned in the section that we discussed the inverse the first time. To illustrate this, we can observe the relationship between the input and output values of y equals 2 to the x power and x equals 2 to the y power, or the logarithmic function y equals log base 2 of x. So if we do that, this is the graph of the function y equals 2 to the x power, while this is the graph of the function x equals 2 to the y power, which is the inverse of that function, or known also as the logarithmic function y equals log base 2 of x. Those are exactly the same. Let's do some observation here. So we observe the following from the graph. From the graph of f of x, when it is equal to 2 to the x power, the y-intercept is 0 and 1, while the x-intercept for the logarithmic function, the inverse of it, g of x equals to log base 2 of x, has an x-intercept at 1 and 0, which is basically a reflection of that point. The domain of the function f of x equals 2 to the x power is all of the real numbers. So the domain of this function is all of the real numbers. As you can see, it is smoothly extending from left to right without any cuts, without any interruptions. And it is the same as the range of the g of x function, which is the logarithmic function or the inverse function, log base 2 of x. So if you observe, the range of this function is from negative infinity to positive infinity. It extends from the bottom to the top with no breaks. Notice also that the range of the exponential function 2 to the x power is from 0 to positive infinity, x inclusive of 0, because 0, when y is equal to 0, that is a horizontal asymptote. This is the same as the domain of f of x, which is from 0 to positive infinity, x inclusive of 0, because the line x is equal to 0 is a vertical asymptote for the logarithmic function. Comparing properties of exponential and logarithmic functions. We're going to have the properties of exponential on this side and the properties of logarithmic functions on that side. For any exponential function that is equal to f of x equals a to the x power, where a is greater than 1, the function is continuous. It's one-to-one function. The domain is all of the real numbers, or from negative infinity to positive infinity. The range is all of the positive numbers, or from 0 to positive infinity, x inclusive of 0. The function is increasing. The horizontal asymptote is the x-axis, or the line y equals to 0. We notice that as x approaches negative infinity, or on the left side of x, the graph will approach the line y equals 0. The y-intercept is 0 and 1. There is no x-intercepts. So we don't have an x-intercept in that case. The logarithmic function, so if we take the inverse of the original exponential function, we will get the logarithmic function x equals a to the y power. In other words, log base a of x, where a is greater than 1. Again, the graph looks like it is continuous, and it is a one-to-one graph. It passes the horizontal line test. The domain is all of the positive real numbers, meaning from 0 to positive infinity, x inclusive of 0. And the range is all of the real numbers, which is negative infinity to positive infinity. There are no horizontal asymptotes, but the vertical asymptote is the line x equals to 0. As x approaches 0 from the right, the graph decreases or drops without a bound. It goes down without a bound. And we do not have a y-intercept, but the x-intercept is 1 and 0. Characteristics of the graph of the parent function f of x equals log base b of x. For any real number x and a constant b that is greater than 0 and b is not equal to 1, we can see the following characteristics in the graph of f of x equals log base b of x. The function is one-to-one function. As you can see here, it passes the horizontal line test. The vertical asymptote is the line x is equal to 0, which is basically the y-axis. The domain is all of the positive real numbers, which means from 0 to positive infinity. The range is all of the real numbers, which means from negative infinity to positive infinity. The x-intercept is 1 and 0, and key point is b and 1. This is a key point, b and 1. The y-intercept, we don't have any y-intercepts. The graph is increasing if the base is greater than 1. So if the base is greater than 1, the graph is going to be increasing. As you can see here, that is where b is greater than 1. If the b is greater than 0 but less than 1, so b is positive, but it's less than 1, the graph is going to be decreasing as follows. So the graph is going to be flipping like that, and it's going to be a decreasing graph, as you can see in that shape. In this figure right here, you will see how changing the base in the logarithmic function can affect the graph. Observe the different graphs here. So the red graph, it is log base 2 of x. And as you can see here, the base is 2. And this is the highest graph. This is the highest graph, or the furthest from the x-axis. And then the natural logarithm of x is the blue graph. And as you can see here, the base is basically the e, which is 2.718282. So it becomes a little bit closer to the x-axis. In other words, the higher the base, the faster the graph is going to grow. Because remember, logarithmic functions are exponential functions. So the growth is going to happen faster, which means the graph is going to become closer to the x-axis as the base increases. Versus the last function, which is log of x, so the base is 10 in that case. Notice how this is the fastest growing graph, which means it is going to be the closest to the x-axis. So we can conclude the higher the base, the closer the graph is going to be to the x-axis. In other words, the higher the base, the faster the graph is going to grow.